So, class L, we're going to talk about, I would call this class the additive law of exponents. Basically talking about how we deal with expressions that are raised to powers. And so I like to start off by talking about what does 2 to the third really mean? We're going to pull up the chat. There we go, that's helpful. Well, I'm sure most of you know that 2 to the third is equal to 8. But why does it equal to 8? What does it mean? Well, it really means 2 times 2 times 2. And that's kind of the whole point. I mean, that's not the whole point, but it's definitely the big idea is that when you talk about exponentiation, right, raising something to an exponent, it's just shorthand notation, right? It's abbreviated notation for that thing multiplied by itself that many times. And in a similar way, 6 to the fourth means 6 times 6 times 6 times 6. No big deal. But then we start having some other things pop up that are interesting. What about 2 to the third times 2 to the fourth? Well, we know what each of those things are supposed to mean. 2 to the third times 2 to the fourth should be 2 times 2 times 2 times 2 times 2 times 2 times 2. Okay, great. How many 2's have we multiplied together? It's 2 to the 7th, which I think you all can see is 2 to the 3 plus 4. And that really is kind of the genesis of what we usually call the additive law of exponents. So here's what we have. Here's the rule. This is the additive law of exponents. And this is true for any base, regardless of if it's positive or negative. So, and again, I would usually use different letters, but your book, I think of the book I was referring to, writes it as a to the r power times a to the s power is equal to a to the r plus s. That's the whole idea. Right? If you're multiplying 3 2's together times another 4 2's together, you're really multiplying 7 2's together. And so you write it as 2 to the 7th. So when you multiply things together, right, I know trig is very different, yes. Don't worry, this will also get a little bit harder. This is not, it's not going to stay just this easy, but you're right. So the whole idea is that when you multiply two things with the same base raised to two different exponents, or even the same exponent, doesn't matter what these are, you can add those exponents together. And that's kind of a big deal. Different bases, nothing, you can't do anything about it, but same base, great. I will actually point out, just because you might be curious, if you do have things with different bases raised to the same power, you can also multiply those together. So if you had something like 2 to the 4th times 3 to the 4th, it is perfectly fine to say that's equal to 2 times 3 to the 4th power. That also works. But that's not where it popped in my head, so that's like I should say. We'll come back around to that. So some examples that are meant to be pretty easy. 3 to the 4th times 3 to the 7th. Again, that's 4 3's multiplied together times 7 3's multiplied together. That's 11 3's multiplied together, or 3 to the 11th power. That's true, Yanquin. I agree. 4x squared equal to 2x quantity squared can be confusing, especially because 4 being 2 squared is also 2 times 2, right? 2 and 4 is kind of extra confusing, but you're right. In fact, we'll kind of address that when we get down here for just a second. So if I had x to the 6 times x to the 8, again, we just get to add the powers. This is x to the 6 plus 8, which is x to the 14th power. Sorry, x is kind of funky there. Yeah, and then something like this, again, it doesn't matter if the base is positive or negative. Negative 2 to the 3rd times negative 2 to the 5th times negative 2 to the 9th. Right, we can have more, we can have multiple terms, not just 2. That's going to be negative 2 to the 3 plus 5 plus 9, which is negative 2 to the 17th. Notice that I'm not actually doing anything worth it. Like you could totally find what 3 to the 11th power is. We don't care really, right? That's not the point. Similarly, we could find negative 2 to the 17th power. That's not really the point. Here we have 3x quantity to the 5th times 3x quantity to the 4th. And there's kind of two ways you can deal with this. Since those bases are the same, you could definitely write this as 3x quantity to the 9th power. But to kind of go with what Yang Kun was saying there, we could also write 3x to the 5th as 3 to the 5th times x to the 5th. And 3x to the 4th as 3 to the 4th times x to the 4th. When you have a product raised to a power, we can distribute that power. If there were only two negative 2's, it would become a positive 2. I'm not sure. We'll come back to that in a second, Jacob. So this would be 3 to the 5th times 3 to the 4th, which is 3 to the 9th, times x to the 5th times x to the 4th, which is x to the 9th. And there was something else I was going to say there, which is that, again, the reason you can distribute this power, right? Like the reason it's true that 3x to the 5th is equal to 3 to the 5th times x to the 5th is because, again, because of what it means, right? 3x to the 5th really means 3x times 3x times 3x times 3x times x. Oh yeah, that's 3 times 3 times 3 times 3 times 3, 3 to the 5th times x times x times x times x times x, x to the 5th. So these rules, what I'm trying to express is these rules aren't just arbitrary, right? They actually work for a reason, and because we need them to work the way they are supposed to work. But I'm trying to kind of show you this is why they work. To answer Jacob's question, oh, sorry. It's a good question, Jacob. I don't mean to call you out. I know it's a direct message. If there were only 2 negative 2's, it would become a positive 2. So let's say, for example, so this one would not be positive because it's a negative number to an odd power. So to be a negative times a negative is odd times a negative is right, or times a negative is right. Times an odd number is negative times an even number is positive. And since this is raised to an odd power, you would end up with a negative result. But I will point out, if you had something like negative 2 to the 10th power, you could say, well, I know since there's an even number of negative 2's multiplied together, that's going to be right, negative 2 times negative 2 times negative 2 10 times. That's going to be positive. So it would be not incorrect to say that this was equal to just 2 to the 10th power. But that's only really true if you have negative numbers raised to even powers, that you can kind of drop the negative sign. And moreover, I wouldn't really stress about it too much. That's probably not such a big deal. Here we have x to the 4th times y times x to the 8th times y to the 3rd. Again, we're just going to combine the like bases. X to the 4th times x to the 8th is x to the 4 plus 8. Y to the 1st times y to the 3rd is y to the 1 plus 3, which is 4. And so whenever you see something that doesn't have a power, the assumed power is the first power. Right? X is x to the 1st, y is y to the 1st, and so on and so on. And then we have one that's not the same. This one I'm going to think of as 2 times 2 times 2 times 2 times 2 times 2 times 2 divided by 2 times 2 times 2. And notably, I can cancel. 2 divided by 2 is 1. 2 divided by 2 is 1. 2 divided by 2 is 1. I'm left with 2 times 2 times 2 times 2, which is 2 to the 4th. Or as you might observe, is 2 to the 7 minus 3 power. So when you multiply things together, we get to add the exponents. When you divide things with, I should say, when you multiply things together with the same base, you get to add the exponents. When you divide things that have the same base, we get to subtract the exponents. So, and I'm just going to put it here because it's really the same rule, just in a different form. So a to the r divided by a to the s is equal to a to the r minus s. Really, I know they don't look the same, but they're really expressing the same idea just in a different way. And please continue to ask questions. You guys are asking great questions. Oh, sorry, my pens are, some of these pens are looking like they might need to be replaced. There are extras over here. New black pen. Should have prepared for this. Okay, come on. There we go. The reason why I think about this working, for example, well, we're kind of okay. So let's look at some examples, like 3 to the 8th divided by 3 to the 6th. If this feels easy, good. Oh, I've got lots of markers back here. Yeah, there's a lot of markers over there. That's not even that many, really. They go fast. I mean, that's all right. So, right, we're just subtracting the power. So this is 3 to the 8 minus 6, which is 3 squared. And again, that's really because in the end, we're just multiplying 3 times 3, right? The 8 3's multiplied together here and the 6 3's multiplied together here. 6 of them cancel out and you're left with just 3 squared. Or you could have something like x to the 23rd divided by x to the 11th, and we're just subtracting. Right? It's not particularly exciting. 23 minus 11 is 12. And things are a little bit more interesting when we have something like this. 2 to the 4th divided by 2 to the 7th. Well, then we subtract and we get 2 to the 4 minus 7, which is 2 to the negative 3rd. And we'll talk about this a little bit more. We need something else kind of first. And then, I think that's plenty of examples. Fine, one more example. Let's say we had, let's do this. Let's do x to the 5th. That's a 5, believe it or not. Let me try it again. X to the 5th times y cubed squared divided by x squared. So 1/2. Yeah. We're definitely 1/2 to the 3rd is where we're going with this for sure. We're going to talk about it a little bit more. So for this one, we would simplify this first as x to the 5th. Oh, you know what? I'm getting a little bit ahead of myself here. I know you guys probably already know where we're going with this, but we'll come back to this one. Let's talk about something important, which is why does 2 to the 0 equal 1? Or really anything raised to the 0th power, right? I mean, it's true for any non-zero number. 6 to the 0 equals 1. -3 to the 0 equals 1. The square root of 2 to the right. Any non-zero number raised to the 0th power is equal to 1. But why? Well, there's a couple of ways of justifying it to yourself. The way I usually think about it is kind of because it has to. Because the additive law of exponents has to work the way we know it does. So check this out. 2 to the 0 times 2 to the 3rd. If I multiply these together and add the exponents, I'm going to get 2 to the 0 plus 3. Okay, but I know what 0 plus 3 is. It's just 3. So my equation is 2 to the 0 times 2 to the 3rd equals 2 to the 3rd. Or if you prefer, 2 to the 0 times 8 equals 8. Okay. Well, what's the only option for that to be? If something times 8 equals 8, that something had better be the number 1. If it's the only option for 2 to the 0, if the additive law of exponents is supposed to work the way it's supposed to work. So this is really why anything raised to the 0th power is equal to 1. Because when you multiply it by something else, the powers add, but since 0 plus anything is just the anything, the power stays the same. And so you've got 1 times 2 to the third equals 2 to the third, for example. And that's kind of the whole story about something raised to the 0th power. Some other people just justify it a different way. You could also say, using the other version, you could say something like, well, hey, I know 5 to the 4th divided by 5 to the 4th. Clearly, that's going to be 1. Anything divided by itself is 1, with the exception of 0, right? 0 divided by 0, not 1. It's undefined, indeterminate. 5 to the 4th divided by 5 to the 4th is 1, but it's also 5 to the 4 minus 4, which is 5 to the 0, which has to be 1. So there's a couple reasons or justifications as to why something raised to the 0th power is equal to 1. And you can kind of do that a bunch of different times, right? There's lots of other ways to show it, but that's kind of it. So we go back to this other side for just 1 second. Some other rules we have. So any base raised to the 0th power is equal to 1. The base should not be 0. So now let's come back to this. Why this, what 2 to the negative third actually is. I say before I look at my notes. Yeah, okay, great. So why is 2 to the negative third equal to 1 over 2 to the third? Well, it's because of the fact that something raised to the 0th power has to equal 1. If you think about it this way, 2 to the negative third times 2 to the third has to equal 2 to the negative 3 plus 3. But negative 3 plus 3 is 0. So 2 to the negative third times 2 to the third equals 1. And then we can divide both sides by 2 to the third and say that 2 to the negative third is equal to 1 divided by 2 to the positive third. And that's another rule that we have. If you have a base to a negative power, it's 1 over the same base to the positive power. Or actually even the flip of that, if you have something raised to a positive power, it's 1 over the same base raised to the corresponding negative power. Or as I like to think of it, whenever you move something from the numerator to the denominator, or the denominator to the numerator, you're really just changing the sign of the power. I guess I should be a little bit more clear there. That's only allowed if you have like multiplication. For example, if you had like 2x plus 1 over x squared plus y squared, you can't just move the x squared up to the top because there's a plus there, right? You can multiply both sides or something, but it's not really helpful. This is more useful if you had something like, I don't know, 2x cubed times y to the 5th over x to the 4th z to the 6th. Then you can bring that z up because you're really just multiplying the top and bottom by z to the negative 6th. Z to the 6th times z to the negative 6, that's z to the 0, which is 1. And then these kind of cancel out. So you simplify this as 2 x to the 3rd divided by x to the 4th is x to the minus 1, y to the 5th times z to the negative 6. And then you start getting into a place of like, well, what's considered simplified? Some people prefer everything not in the denominator. Some people would prefer you wrote this as 2y to the 5th divided by x times z to the 6th. I will try to be clear with instructions about what I want. A lot of the time people ask for all the powers to be positive powers. That's a very typical way of answering a question like that. Sure. So some more examples. Again, these are going to, I feel like it's a little repetitive, but it's good, right? It's good to be repetitive. So 5 to the negative second would be 1 over 5 squared. Or -3 to the negative fourth, we could definitely write as 1 over -3 to the fourth. And to go back to someone else's point, technically it would be 1 over 3 to the fourth as well, because a negative number to an even power ends up being positive. Either way, this is equal to 1 over 81. Again, I don't want you to think too much about that, right? It's not a big deal. Like I would just leave it like that, but it is true. If you have a negative to an even power, you can get rid of the negative. Yeah. I feel like I kind of left something off. Let me take a quick look here before I get. Oh, I know, it's still coming up. Yeah, okay. I want to get to something else, but we're not there yet. So yeah, now we get to the fun part, the fractional exponents. So can somebody tell me, either with your words or in the chat, what 9 to the 1/2 is?
Is it 3?
It's definitely 3. You guys are all right on. Okay, but now I'm going to ask. Well, I'm going to ask and kind of answer a different question. We said 2 to the third meant 2 times 2 times 2. Right, because it's repeat multiplication. But 9, when you have powers that are not integers, it kind of loses some of the meaning. And 9 to the 1/2, like, so 9 times itself a half a time. I mean, that's kind of what it is. So here's the way I kind of envision it, or how we figure it out. We know this is true, right? We know it's a square root, but why does it work? Well, again, all these things work because of the additive law of exponents. I'm going to say it like 1,000 times. The additive law of exponents, again and again and again. If you take 9 to the 1/2 and you multiply it by 9 to the 1/2, well, when you add those powers, what do you get? What's a half plus a half? I know you all know. It's 1, right? Thank you. Okay, so we're looking for a number multiplied by itself that's equal to 9. Well, this number has to be 3. That's why 9 to the 1/2 is equal to 3. Or that's why the 1/2 power is the same as the square root. When you take a 1/2 power of something, you're saying, oh, what do I do? What do I get when you take something and you multiply by itself to get that thing to the first power? And so I should also address, right, whenever you're taking even roots or even fractional powers, we always define it to be the positive root. So if you were asking me what number, really we're asking what positive number multiplied by itself is that? And the answer is 3. Some notation stuff. So yeah, 9 to the 1/2 equals 3, because 3 times 3 equals 9. And yeah. Something else I wanted to mention here. Some other notation stuff, as I'm sure you are probably aware, 9 to the 1/2 we also write as the square root of 9. Some people like to throw a 2 in there. I don't particularly care for that, and most people don't, but sometimes people write it that way. It's kind of similarly, we can say that 25 to the 1/2 power is equal to 5, because 25 to the 1/2 times 25 to the 1/2 should equal 25 to the 1. So whenever you're taking a square root, you're really just asking, or whenever you're taking a 1/2 power of square root, you're just saying, oh, what number multiplied by itself equals the base? 25 in this case, 9 in that case. Which doesn't feel super interesting so far, but it gets more interesting when we talk about different fractional powers. I kind of want to leave that stuff up. Yeah, I'm going to leave that stuff up. So what if instead of a 1/2 power, I want to find, say, 8 to the 1/3 power? Well, I'm looking for a power that if you multiply, well, I can do 8 to the 1/3 times 8 to the 1/3 times another 8 to the 1/3. And 1/3 plus 1/3 plus 1/3 is also 1. So now if you're trying to find 8 to the 1/3, you're looking for a number multiplied by itself, not 2 times, but 3 times to get you to 8. And that number happens to be 2. 2 times 2 times 2 is 8. So 8 to the 1/3 is equal to 2. Or if you prefer, you could say 8 to the 1/3 is the cube root of 8, and it is equal to 2. I feel like I keep grabbing like the wrong, not as good pen. Maybe they just both are not excellent. They both look pretty good. Oh, that one's way empty. Okay. So another kind of rule to be aware of, or no, this is more notation than a rule. A to the 1/n power is the same as the nth root of A. And I will tell you a lot, once you start taking calculus and start taking derivatives of things, it is often much more convenient to write something using this notation than it is to use this notation. So a lot of times you want to change a cube root into something to the 1/3 power, for example. Let's look at another example. How about 81 to the 1/4 power? Well, I don't want to write it all out. I'm just going to say, we know that 81 to the 1/4 is the 4th root of 81. And that's going to be 3. And the reason it's 3 is because we know that 3 times 3 times 3 times 3 is 9 times 9, which is 81. So whenever you're trying to find a something root, like a 4th root of a number, you're looking for the smaller one, the other number, that if you multiply it by itself that many times, you end up with the base you started with. You could also say, right, 3 is 81 to the 1/4 times another 81 to the 1/4 times another 81 to the 1/4 times another 81 to the 1/4. And when you multiply those together, the 1/4 powers all add up because of the additive law of exponents to a positive one. Yeah, a few more things. So I know I alluded to this before, but I'm going to say it again. When you have a product or a quotient, so anything, group of stuff multiplied or divided together, raised to a power, you can distribute that power. So for example, something like 2 times 3 squared is 2 squared times 3 squared. And you can see it in either way. You can say, well, okay, 2 times 3 squared is 6 squared, which is 36. Or 2 squared times 3 squared is 4 times 9, which is 36. Oh yeah, they're the same. And it's true whether you're doing division or multiplication. So you could say something like, well, in fact, the example I was looking at before, I don't remember exactly, I'm going to make up something similar. It was something like x squared y cubed to the 4th power divided by x to the 6th y to the 2nd. You can say, oh, there's still something. I keep wanting to do this problem. There's like, oh, there's still one more thing we need. Okay. Well, in fact, we'll just do it now. So x squared times y cubed to the 4th is going to be x squared to the fourth times y cubed to the fourth over x to the sixth times y squared. Now, sorry, 1 second. What's x squared to the fourth? So now I'm getting ahead of myself a tiny bit. Yeah. In fact, let's come back to this one in just a second. I bet many of you know what x squared to the fourth is, but let me talk about a power to a power. So what if we had 2 to the third to the fourth? How many 2's are we multiplying together? Well, 2 to the third to the fourth means 2 to the third times 2 to the third times 2 to the third times 2 to the third. Right, that's 2 to the third raised to the fourth power. But then we know what 2 to the third is. It's 2 times 2 times 2. So I've got a lot of 2's. 2 times 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 2, which is how many 2's? Looks like I got a dozen. 2 to the 12. Or as you might observe, it's 2 to the 3 times 4 power. And that's what happens when you have a power to a power. You end up multiplying the powers. So here, if you had x squared to the fourth, that would really be x to the 2 times 4. Because it'd be x squared times x squared times x squared times x squared, which would add up all the squares, and 2 plus 2 plus 2 plus 2 is 8, which is exactly what you're going to get there. And y to the third to the fourth is going to be y to the 12th. And then we've got an x to the 6th on the bottom, and a y squared. And then that's an x to the 8th. So x to the 8th times y to the 12th over x to the 6th times y squared. And then we would subtract the powers. X to the 8th divided by x to the 6th is going to be x to the 8 minus 6. And y to the 12th divided by y squared is going to be y to the 12 minus 2. And that's how we'd simplify something like that. So let's look at a few more examples. Actually, let me write down a couple more things. I just keep adding things to my list over here. So we also have that if you have a power to a power, so a raised to the r power raised to the s power, that is equal to a to the r times s. And I will also point out it's also equal to the other way of writing it. A to the s to the r power is equal to a to the s times r. But s times r and r times s are the same. So these are actually equal to each other. That is getting a little out of control over here. And then we also have a times b to the, what notation did I use in my notes? Sure. A times b to the r is a to the r times b to the r. And also a divided by b to the r is a to the r divided by b to the r. So what I want to say about this particular rule here is that when you have a product, basically multiplication or division doesn't work for addition or subtraction. When you have multiplication or division all raised to a power, you can distribute that power. So it is totally, perfectly cool. Say something like, x cubed times y squared to the third power is equal to x to the third times y to the second to the third. But I want to make it super duper explicit. Right? It is not okay to say something like x plus y squared is equal to x squared plus y squared. That is not true, because we can't distribute powers across addition. We can only distribute powers across multiplication or division. So in a similar way, if you had 2x divided by 7y squared, it'd be perfectly fine to write that as 2 squared times x squared over 7 squared times y squared, which would be 4x squared over 49y squared. I will also mention there are a lot there, so I'm not doing every single example in the notes because there's a lot of them, but I am doing most of them. So, but if you want to look for other examples, there are certainly some there. Sure. Sure. So someone asked how to write. So I'm not sure if it's square root of 5 times x squared, or if I'm missing some parentheses, or if the x is in the square root. I'm not really sure. All in the radical. Sure. So the square root of anything, as long as it's positive, squared is just, well, we can, so I'm going to use the power to power. So let's rewrite the square root as a power. That's 5x to the 1/2 power squared. And then when you have a power to a power, what do we do with the powers? We multiply them. And 1/2 times 2 is 1. So this is 5x raised to the first power, but then anything to the first power is just itself. So this is just 5x. Someone asked how to solve x plus y squared, and I'm not really sure exactly what the question is, because if you're solving something, it's usually an equation where it's equal to something else. I can talk about how to expand x plus y squared. So x plus y squared would expand as x plus y times x plus y, which is x times x, which is x squared. I will also mention, just because I feel like people get caught up with this a lot, when someone says something is squared, it literally just means it's multiplied by itself. So someone says we're squaring a thing, you should be like, oh, we're just multiplying it by itself. That's all that means when someone says something squared. And then we have x times y. And then we have y times x, which is also the same as x times y. And then we have y times y, which is y squared. And then we usually simplify this as x squared plus 2xy plus y squared. And I just want to really emphasize here, right? This is not the same as x squared plus y squared. People often say if you do this the wrong way, that you're missing the middle term. You're missing the 2xy if you just try and square each part. When do you factor and when do you distribute? Well, I mean, they're so I think factoring is kind of the opposite of distributing. Right? I said I was factoring this out or foiling it out, as people say, but this is distributing, right? I'm distributing the x to the x and y, and I'm distributing the y to the x and y. So I'm just distributing each. So really what I'm doing is I'm writing this as x times x plus y plus y times x plus y, and then distributing like that. That's kind of what's happening there. So how much time have I got? I got 10 minutes. Okay. So there's a couple examples of powers to powers that I think I'm going to skip because I feel like I imagine. So there's a couple things I got to get to before I can take homework. I'm happy to look at stuff after class, but there's one more topic I need to for sure talk about before I can do other things. So let me just do one more example and then one other thing, and then yes, certainly after class. So let's say we had something like, what do I got here? 3x to the 4th over y to the 1/2 times b to the 5th to the 6th power. If I was trying to simplify that, I would raise each part to the 6th power. So that would be 3 to the 6th times x to the 4th to the 6th divided by y to the 1/2 to the 6th times b to the 5th to the 6th. And then for all these powers to powers, we're going to multiply. 3 to the 6th is just 3 to the 6th. We could multiply it out. It's kind of a big number. It's 729. I don't think it's necessary to multiply it out. But x to the 4th to the 6th, we should definitely simplify as x to the 24th. Y to the 1/2 to the 6th, well, 1/2 times 6 is 3. That's going to be y to the 3rd. And then 5 times 6 is 30, so we're going to get b to the 30th. So that's how we would simplify something like that one. Cool. So let's look at some other. I think I'm finally going to erase all these rules. So we can also look at fractional powers. In fact, we already looked at a couple, right? We looked at 81 to the 1/4 and saw that it was equal to 3. But I'm going to write it in a special way. I'm going to write it as 3 to the 4th to the 1/4. Right? 81 is 3 to the 4th power. And then these powers to powers, oh, that's 3 to the 4 times 1/4, which is 3 to the 1, which is 3. No one would ever write all that out normally, but it's a way that helps us kind of see what we're going to get. In a similar way, 32 to the 1/5, or the 1/5 power of 32, or the 5th root of 32, is going to equal 2, because 32 is 2 to the 5th. And 2 to the 5th to the 1/5, well, that's 2 to the 1, which is just 2. So when you take, say, the 5th root of something, you're asking yourself, oh, what do you multiply by itself that many times to get the original number? In the same sort of way, we could ask, what's the cube root or the 1/3 power of -27? Okay, well, what do you multiply by itself 3 times to get -27? -3. And this is -3 to the 3rd to the 1/3. -3 to the 3rd is -27. Right? -3 times -3 is 9 times -3 is -27. And so that's going to be just -3 to the 1, which is -3. I should mention, when you have fractional powers with odd denominators, you can take a fractional power with an odd denominator of a negative number. Or another thing, you can take odd roots of negative numbers. Another example would be like the cube root of -8, or -8 to the 1/3 power is -2. Because -2 times -2 times -2 is -8. In fact, I should write that down. We cannot find even roots of negative numbers. For example, the square root of -9, the 4th root of -81, the square root, I don't know why I'm writing 2 there, of -25. All of these are not real, right? They're complex or imaginary. But I do want to point out, we can find odd roots of negative numbers. Like we just did. The cube root of -8 is -2. The cube root of 8 is +2. Or the, I don't know how long, the -27. But the cube root of -27 is -3. And the cube root of 27. So for odd roots, if you know what the positive odd root is, you know what the negative root is. Okay. And again, the reason something like this doesn't work is because negative 25 to the 1/2, which is what that is, well, if you want to multiply it by itself to get negative 25 to the 1, there isn't a real number that you can multiply by itself and have it turn out negative. Positive times a positive is positive, negative times a negative is positive. So this doesn't work. This leads to imaginary numbers, which we're not talking about yet. All right. A lot of umming today. Something else important, a mistake I see a lot, and I want to help you avoid, is that 4 squared, for example, is equal to 4 times 4, which is 16. It is not 4 times 2, which is 8. So be careful. Right? I see that mistake. Not, I don't think very much in this class, but just in general, my math career, I still make this mistake a lot. So try not to. All right. Last thing I want to talk about are fractional powers that are more complicated. So something like 8 to the 2/3 power. If I want to do 8 to the 2/3 power, I'm going to break it up so it looks like a power to a power. And when you have a fractional power like this, where the numerator and the denominator are both not 1, you have choices. One choice is to write it as 8 squared to the 1/3 power. And that's perfectly fine. That's going to be 64 to the 1/3 power, and the cube root of 64 is 4. Or you could do it as 8 to the 1/3 squared. 8 to the 1/3 is 2, and 2 squared is 4. And the nice thing is, no matter which way you do it, it's going to turn out right. The not nice thing is that if you do it one way versus the other, sometimes it's much worse. For example, 9 to the 3/2 power. You could totally do 9 to the 3/2 as 9 to the 1/2 cubed, which is the easier way. That's going to be 3 cubed, which is 27. You could also do it as 9 cubed to the 1/2 power. But most normal people don't know what 9 cubed is off the top of their head. I'm not normal. I've seen this problem a lot. 9 cubed is 729. But I don't know the square. Well, I don't know just looking at what the square root of 729 is, but I know that since this and this are supposed to be equal, the square root of 729 should be 27. But I hope you can all agree that doing it this way is much better than doing it this way. Or more generally, you always want to do the denominator part of the fractional power first, or the root part first. So if I was doing something like 125 to the 2/3 power, and 5 cubed is 125, you would definitely want to do this as 125 to the 1/3 squared, because the cube root of 125 is 5, and 5 squared is 25. Let me just do one more. I got a minute, and then I can look it up on. So if you want to do something like 8 to the negative 2/3, I would ignore the negative until the very end. Or what I would really do is I would write it as 8 to the 1/3 to the negative 2. Right? Negative 2/3 is definitely negative 2 times 1/3. And then 8 to the 1/3 power is the cube root of 8, which is 2. Now I've got 2 to the negative second. And I know a negative power just gives me a flip. It's 1/2 to the positive second. I wouldn't normally write the positive side. And that's going to be 1/4. Okay, I think, well, I definitely know that's all the time I have, but let me go ahead. So, as is typical, that's all there is for class. You all are welcome to leave if you want. I will not keep you longer than I'm supposed to. But let me answer the couple questions I got from people in the messages. So somebody asked if I could look at 1L from the homework or an example like it. Sure, let me just grab the homework real quick, and then I can look at the other question I just got as well. 1L. Oh, gnarly. Oh, that's not as bad as it looks. But yeah, let me make up one. I don't really care, but I'll make up a slightly different one just to make it seem like I'm not showing you exactly how to do it. So here's one similar to 1L. Let's look at, say, the 7th root of, be a little bit careful here, 8 to the 7th cubed, sure. Okay, so here's the thing. The root, I want to rewrite the root as a power. So instead of the 7th root of 8 to the 7th, I'm going to rewrite this as 8 to the 7th to the 1/7, all to the 3rd power. Those are the same. And so then we can see, oh wait, 8 to the 7th to the 1/7, if I multiply those powers, I'm going to get 8 to the 7 times 1/7, which is just 8, sorry, to the 3rd, which is 8 to the 1 to the 3rd. We didn't really have to write the 1 anymore. That's just 8 to the 3rd, which is big enough that I feel like you don't need to multiply it out. But if you did want to multiply it out, you would get that was 512. Anyone who's played one of those dumb little games on your phone that's like the 2, 4, 8, 1024 games, you should know all these powers of 2 numbers. 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, right? My wife was playing a different one the other day, and she got up to like, she got a block that was like 130,000 or something. Here's what I would say about that question. So 8 to the 7/7 isn't wrong, but it's not as simplified as possible. So 8 to the 7/7 is correct, but 8 to the 7/7 is 8 to the 1st, which is just 8. Cool. And then somebody else asked about, what if it was like y to the 1/2 to the 7th? Yeah, an exponent can be a decimal. So if you had like something like y to the 1/2 to the 7th, I will tell you my preference is usually a fraction. I would probably write this as y to the 1/2 times 7, which is y to the 7/2. But it is also perfectly legitimate to write it as y to the 3.5 power. That is also perfectly acceptable. The issue I will point out is that sometimes your denominator doesn't divide nicely. For example, if instead you had like x to the 1/3 to the 7th, which is x to the 7/3, there's no nice way of writing that with a decimal, right? No one, I really would encourage you to not write that as x to the 2.33 repeating, right? That just seems a little silly. So you should, this would technically be correct, but it would be better to write it as this. So that's why oftentimes people don't use decimals in their exponents, because they're not very nice.